MOSS Audio Technical Report.
Here we go.
Yeah, no preamble today. Welcome to AI Paper Slop. Today we're looking at a foundational AI that doesn't just, read a transcript of what you say.
Right. It actually listens to you.
Exactly. It listens to you breathe, it pauses when you sigh, and it actually knows what complex jazz chords are playing in the background, all processed in one single pass.
It's massive.
It really is. So for the ML engineers or the researchers out there listening, here is your 60-second core insight summary. Let's get straight into it.
Give them the pitch.
So MOSS Audio is a unified audio language model. It handles speech, environmental sound, and music completely under one roof.
Yeah, no separate pipelines.
Right. And it comes in these 4 billion and 8 billion parameter sizes. They have Instruct variants for like direct tasks, ASR, and thinking variants for the really complex reasoning stuff.
And the underlying mechanism, the secret sauce here, is that it relies on a 12.5 hertz temporal representation.
12.5 hertz, yeah.
But what really sets it apart is how it actually cracks the code on context loss. They use two main innovations.
Which are huge.
Yeah. First is DeepStack cross-layer feature injection. So instead of just giving the LLM decoder the final layer of audio features, it feeds it multiple depths of features.
We'll dig into why that matters in a second.
Right. And the second innovation is they interleave explicit time markers directly into the token stream.
So it's not guessing about time. Add to that a massive pre-training diet of 1.2 trillion tokens.
Trillion with a T.
Yeah, filtered through a really unique event-preserving segmentation pipeline. And, well, you have a model that fundamentally changes how we handle sound.
We're finally, moving past that era of treating audio as just an ASR to text pipeline.
Thank goodness. I mean, this model actually understands prosody, transient events, and really complex acoustic environments.
It's a true multimodal understanding.
Exactly. So now that you know what it does, let's break down the architecture. Let's talk about how it processes sound without losing all those granular details.
Right, starting with the audio encoder.
Yeah, it's a dedicated 0.6 billion parameter audio encoder. And they built this entirely from scratch.
Which is no small feat.
Not at all. It ingests these 128-channel log-mel spectrograms and then applies an 8x downsampling to hit that 12.5 hertz token rate you mentioned.
And that token rate, that 12.5 hertz, it's basically the foundational heartbeat of the whole model.
Right.
It translates to the encoder spitting out 12.5 tokens for every single second of audio.
Which is pretty compressed.
It is. But the brilliance isn't just in the compression rate. It's really about how they manage the attention mechanism inside that encoder.
Oh, the sliding window attention.
Exactly. Because in standard models, global self-attention scales quadratically.
Yeah, it blows up.
Right. If you feed a standard model a 10-minute audio file, the memory requirements just explode.
Yeah, if you've ever tried to run inference on a long audio file, you just watch your GPU instantly spit out an out-of-memory error.
No, absolutely.
The KV caching is the bottleneck. The key value states will just, eat your VRAM for breakfast.
They really do. So to solve this, MOSS Audio's encoder restricts attention to a sliding window of a maximum of 100 frames.
And at 12.5 tokens a second.
100 frames is exactly an 8-second window.
Got it.
So by limiting the attention to just this local neighborhood, the memory footprint stays constant. It doesn't matter if the audio file is 10 seconds or 10 hours.
That's incredibly smart. So the encoder handles the immediate acoustic modeling, the phonemes, the timbre, like the attack of the snare drum.
Right, the locus stuff.
Yeah. And then it gracefully delegates the long-range semantic reasoning to the language model backbone.
Exactly. Which brings us to the first major architectural innovation here, DeepStack feature injection.
Yeah, this is cool. So think of it as standard audio encoder's output, like the final mixed master track of a song, right?
A great analogy, yeah.
Thanks. So all the raw stems, the isolated vocals, the drum tracks, the bass line, the room noise, by the time they reach the top layer of a standard encoder, they're completely baked together into one flat file.
Right, you can't unbake the cake.
Exactly. Standard pipelines only feed that final mixed master layer to the language model. So you can't easily isolate the hi-hat anymore. The subtle details are just gone.
And this gets to the physical reality of how transformers process data. As audio passes through the deeper and deeper layers of an encoder, the network inevitably drifts toward lexical and semantic meaning.
It's trying to figure out the words.
Exactly. The loss functions naturally push those deep layers to abstract the raw sound into concepts. It filters out the noise, but in doing so, it strips away the actual acoustic reality.
The tone, the emotion.
Yeah.
So DeepStack essentially gives the language model access to those raw multi-track stems again.
Right.
MOSS Audio extracts the intermediate hidden states from various depths of the encoder. It routes them through a merge adapter and then just injects them directly into the early layers of the decoder.
It completely preserves the multi-level acoustic evidence because the lower and intermediate layers are where the prosody lives.
Right, the emotion.
Yeah, it's where the subtle tremor in a voice or those short background events or the specific resonance of a room are calculated.
Wow.
DeepStack ensures the decoder gets this multi-granularity view of the audio, and it does it without having to build a completely separate, bloated encoder just for environmental sounds.
So DeepStack solves the problem of lost acoustic details. But once you have all those rich multi-track stems flooding into the decoder, you had a totally different physics problem. Time.
Right, temporal drift.
Yeah. Over a long sequence, the model's internal clock just starts to drift because standard models usually just rely on relative positional embeddings, right?
Yeah, the model basically just infers where a token is based on its sequential distance from the other tokens.
Exactly, which is why MOSS Audio's second big architectural pillar is explicit time markers.
This is such a simple but brilliant fix.
It really is. They literally insert elapsed time numerical markers, like the numbers 2.0, 4.0, 6.0, directly into the text token sequence.
Right into the stream.
Yeah, they drop these markers into the stream after every 25 audio features.
And because the token rate is 12.5 hertz, 25 features is exactly 2 seconds of real elapsed time.
Right. But let me push back on this for a second just to play devil's advocate.
Sure.
If the model is already fundamentally built on this strict 12.5 hertz token rate, why can't it just implicitly figure out the timeline? Like, isn't counting tokens enough to know what time it is?
Well, I mean, in a perfect vacuum, maybe.
Okay.
But in practical, autoregressive generation, relying on implicit token counting completely fails over long sequences. The model's internal sense of timing gets blurry.
It just loses track.
Yeah. So when you want to execute timestamped ASR, where you need the exact millisecond, a specific word was spoken.
Right.
Or if a user asks a time-aware question like, hey, what was that sudden metallic sound at 2 minutes and 14 seconds?
Oh, I see.
The model needs a hard anchor. It needs to know exactly where it is.
So it's like passing absolute memory addresses in a massive distributed data array. Instead of just telling the system, just look 3 blocks over and hope nothing shifted.
That is a highly accurate way to frame it, yeah. Explicit grounding gives it an absolute reference point.
So it prevents compounding temporal errors.
Exactly. The token stream has absolute timestamps interleaved right alongside the audio data. So the model learns timestamp generation directly through standard text generation.
That is incredibly elegant. But, an architecture that can process all this granularity is totally useless if it doesn't have the ground truth to actually learn from.
Oh, completely. The data is everything.
Right. So let's shift from the architecture to the data engine.
Yeah.
Because the team built a massive, highly complex pipeline to generate heterogeneous supervision.
Yeah, and they tackle a problem that basically every ML engineer hates, segmenting the training audio.
Oh, the worst. Because standard datasets usually just arbitrarily chop audio into fixed 10-second or 30-second windows.
Right, it's just a mathematical cut. It has absolutely zero respect for the content of the audio.
Which is terrible for contextual learning.
Yeah.
Imagine someone is halfway through a complex word, or, I don't know, a dog mid-bark.
And the pipeline just slices it right in half.
Exactly. The model learns these fragmented, corrupted representations of those sounds.
Yeah, so MOSS Audio just completely ditches fixed windows. They use event-preserving segmentation.
Okay, how does that work?
They run a frame-level sound event detection model, specifically beats.
That's bidirectional encoder representation from audio transformers.
That's the one. They use it to map out natural event boundaries. It analyzes the audio frame by frame to find natural pauses.
So it's actually looking for silence?
Yeah. And it merges vocal events with the gap tolerance, so complete speaker turns stay completely intact.
That is so much better. But what I find really fascinating is their heuristic for ambient background noise.
Oh, the 60-second rule.
Yeah. If an ambient noise like, say, wind blowing or a low engine hum lasts longer than 60 seconds, they just exclude it from the boundary calculations entirely.
Which makes sense, logically.
It totally does. If a low hum lasts longer than a minute, It's not a discrete event anymore. It's a persistent environmental condition.
Right, it's just the room tone at that point.
Exactly. You don't want to define your segmentation cuts around it.
So once the audio is naturally segmented, they route it into 3 specialized annotation branches to generate the actual training labels.
Right. Let's walk through those. The first branch is strictly for speech.
Okay.
And they don't just rely on one single transcriber. They use a multimodal ASR consensus approach.
Which is smart.
Yeah, if the different transcription models disagree, meaning there's a high word error rate between their outputs, they just drop the data entirely.
Wow, that's a brutal quality filter.
It is, but it guarantees high-quality labels. Then, for temporal grounding, they use the Torch Audio MMS forced alignment model.
And force alignment is basically taking a text transcript and precisely matching it back to the acoustic waveform, right?
Yep, to get exact word-level timestamps. Plus, they run diarism, which handles speaker diarization.
Oh, nice.
So the dataset explicitly labels exactly who is speaking and when they take their turn.
That's incredibly thorough.
It really is.
And then the second branch handles general audio. This represents the messy, overlapping reality of real-world sound.
The cocktail party problem.
Exactly. They use Qwen3 Omni Captioner to establish global semantic anchors, and they pair that with local frame-level event metadata.
And this is where the synthetic data generation comes in, which I think is crucial. They use a method called TAC timestamped audio captioning.
Right, because annotating overlapping real-world sounds is basically impossible for human labelers.
Completely. If a dog barks exactly as someone emphasizes a vowel and a car drives by at the same time, a human just can't mark those overlapping millisecond boundaries accurately.
That's too dense.
Yeah, so the pipeline synthetically composites isolated sound effects and backgrounds with explicit layouts and timestamps.
So it gives the model perfectly controlled multi-granularity data for dense caption supervision.
Exactly. It completely solves the overlapping sound issue.
And then the third branch is dedicated to music. And they move way beyond generic tags like, upbeat pop.
Oh, I love this part.
Yeah, they deploy rigorous music information retrieval tools. They use Cordino to map harmonic structures, JukeMirror for acoustic features, and Songformer to detect large-scale arrangements.
Like verses and choruses.
Exactly. Verses, choruses, tempos. They extract the actual structural evidence of the music and merge it with holistic captions.
But listen, this introduces a massive formatting headache.
Oh, a nightmare.
Right. You have exact word-level speech timestamps, synthetic bird chirp coordinates, and musical chord progressions all in one data set.
How do you train a unified model on all that disparate metadata without the loss function just tearing itself apart?
Right. So they solve this formatting chaos with their router R1 merging policy.
Okay, router R1.
First, they apply canonical normalization. This projects all the different structural outputs into a unified JSON-style interface.
Makes sense. Make it all look the same.
Yeah. And then router R1 analyzes the data to decide which branches of evidence to actually include in the final training label.
How does it decide?
It uses entropy and uncertainty scores. It's designed to be deliberately conservative.
Meaning it's cautious about what it includes.
Exactly. It wants to keep weak but meaningful signals, like a faint background song, playing during a conversation. But it utilizes those uncertainty scores to aggressively drop hallucinations.
So if the model isn't sure, it just leaves it out.
Right. If the speech prior confidence is practically zero, it suppresses any speech-related claims. It synthesizes all of this into one clean, unified English description.
That's brilliant. So with a data dynamically labeled and normalized, we can finally look at the actual compute strategy.
The training recipe.
Yeah. The pre-training diet consists of 1.2 trillion tokens, and the ratio here is highly specific.
What's the breakdown?
It's 30% ASR-related tasks, 40% holistic audio captioning, and 30% text-only language modeling.
Okay, let's pause on that. That 30% text-only allocation is vital.
It really is.
If you're building an audio model, you might wonder why nearly a third of the pre-training is just pure text.
Right, why not just all audio?
It's to prevent catastrophic forgetting. The language model backbone already knows how to write code, how to do math, how to reason logically.
Yeah, it has world knowledge.
Exactly. If you just bombard it with 1.2 trillion tokens of nothing but audio transcriptions and sound captions, the weights shift so drastically that it loses its general intelligence.
It forgets how to think.
Right. Mixing in pure text preserves that foundational reasoning capability.
Makes total sense. So they execute this pre-training in 2 stages. Stage 1 freezes the LLM entirely and only trains the adapters.
Just getting them to talk to each other.
Exactly. The goal is simply to get the audio encoder speaking the same representational language as the text model. And then stage 2 unfreezes the system and trains everything end to end.
And once pre-training is done, the pipeline moves to post-training.
Right.
This starts with supervised fine-tuning, where the model learns instruction following. But then, and this is so cool, they inject a highly specialized dataset called Reasoning Cold Start.
Oh, right.
They use both audio and text-only data to teach the model how to basically show its work.
Like chain of thought.
Exactly. It's not just about blurting out the final answer. The model learns to explicitly connect its final conclusion to the acoustic evidence it actually heard, step by step.
Which initializes stable reasoning behavior, and that sets the stage for the final and really the most complex phase, reinforcement learning.
DPO.
Yes, DAPO, direct preference optimization.
So let's spend some time unpacking this DAPO stage, because their use of dynamic filtering here feels deeply counterintuitive when you first read the paper.
It definitely breaks some conventional RL rules.
Yeah. So during this phase, the system samples 16 different generated responses for a given prompt.
Right.
But the team specifically drops entire rollout groups if the reward standard deviation across those 16 responses is 0. Wait. If the model gets 16 out of 16 rollouts, perfectly right. Or if it fails completely on all 16, you just throw that data away.
Yep.
But isn't that perfectly good data demonstrating mastery or failure? Why drop it?
So let's unravel the paradox here, because in policy optimization, keeping that unanimous data is actually highly inefficient.
Really?
Yeah. If the reward standard deviation is 0, it means all 16 trajectories receive the exact same score from the reward model.
Okay.
So there is no within-group advantage signal. The gradient update you would get from that batch is effectively meaningless for preference optimization.
Oh, because the model learns by contrasting a good response against a bad response for the exact same prompt.
Exactly.
If the score is unanimous, the algorithm has absolutely nothing to contrast. It teaches the model nothing new.
Precisely the point. By actively dropping those zero variance groups, the filtering system forces the compute to focus strictly on the hardest prompts.
The edge cases.
Yeah, the edge cases where the model is on the fence, generating some good rollouts and some bad ones. That's where the learning actually happens.
That is so efficient. And the math in the paper backs this up beautifully. Because they are aggressively dropping so many easy groups as the model gets smarter, they actually have to run extra oversampling rounds just to refill the training batch.
Right, to get enough useful data.
Yeah, the charts show this scaling up dramatically. They go from 1 extra sampling round early on all the way up to 14 extra rounds per step-by-step 139.
It's a brutal filtration system, but the results completely justify it.
They really do.
The dynamic filtering kept the model's response lengths completely stable.
Oh, that's huge.
It is. It means the model didn't just learn to game the reward system by writing longer, more verbose essays, which is a really common failure mode in RL.
Right, the verbosity bias.
Exactly. Meanwhile, the raw reward score increased steadily, peaking at a highly robust 0.847.
Wow. So what does this culmination of architecture, massive data filtering, and reinforcement learning actually look like in practice?
Let's talk benchmarks.
Yeah, let's talk about the results. How does MOS audio actually measure up against the rest of the field?
Well, we have to evaluate the two different variants independently, right? The thinking variants and the instruct variants.
Right.
Starting with the thinking variants, which are available in 4 billion and 8 billion parameter sizes.
The 8B thinking variant absolutely dominates the open source models on general audio understanding.
He really does.
We're looking at massive multidiscipline benchmarks like MMAU and MAR.
Yeah.
These test the model on everything from complex music theory analysis to like vehicle engine diagnostics based on sound.
And the 8B thinking model hits a 71.08 average.
Which is wild.
And what's truly impressive is the scaling efficiency they achieved. Even the smaller 4B thinking variant outperforms many 8 billion. And in some specific multimodal reasoning tasks, it even beats 30 billion parameter open source competitors.
That's punching so far above its weight class.
It really is.
But if we look at the Instruct variants, the paradigm kind of shifts.
Yeah.
The thinking models are built for deep, multi-step chain of thought reasoning. But if a developer just needs direct execution like transcribe this audio or give me a dense caption of this soundscape, the Instruct variants actually perform better.
The 8B Instruct model leads the pack in fine-grained speech captioning.
Right.
They evaluated this across 13 distinct dimensions. We're talking gender, age, regional accent, pitch, emotion, and voice texture.
Voice texture.
Yeah. And the 8B Instruct beat proprietary closed-source models like Gemini 3.1 Pro on this benchmark.
We can connect the why directly back to the architecture we were talking about.
Absolutely.
It beats models like Gemini, specifically on evaluating voice texture, because the DeepStack architecture preserved those raw, low-level acoustic layers.
Exactly.
Standard pipelines just completely filter out that acoustic reality before it ever reaches the language model.
Yeah, DeepStack is doing the heavy lifting there. The Instruct variant also excels at time-stamped ASR. They measure this using accumulated average shift, or AAS.
And what exactly does that measure?
So ASS calculates the average absolute time shift in milliseconds between the model's predicted timestamp and the actual reference timestamp.
Okay, so lower is better.
Exactly. And the 8B Instruct achieves the lowest shift across the board, meaning it places the transcribed words on the timeline with incredibly high millisecond precision.
Which goes back to those explicit time markers.
Exactly. It all ties together.
It really does.
Yeah.
So what does this all mean for the developers and engineers listening right now?
The paradigm shift.
Yeah, the core paradigm shift here is that MOSS audio proves you don't need a fractured multi-system pipeline anymore. You don't need one model running heavy inference for transcription, and then routing that text to a separate sentiment classifier to tell you if the user is angry, while, like, a completely different audio classifier tries to tell you a dog barked in the background.
It's all too clunky. You can deploy a single autoregressive text generation framework that inherently understands both the semantic what and the temporal when of highly complex real-world audio.
Which leads us to a final sort of provocative thought regarding the future of AI architecture.
Let's hear it.
If a foundational model can jointly reason over the lexical content of what someone is saying, the prosodic emotion in their voice, and the environmental context happening in the background all simultaneously,
Yeah.
how does this fundamentally change the way you should be designing the state machines and tool use triggers for the next generation of real-time voice agents?
Oh, it changes everything. If the agent can literally hear a user hesitate, or take a sharp breath, or sigh in frustration before they even finish their sentence, relying on a standard text-based LLM pipeline to trigger a response is suddenly entirely obsolete.
You're no longer just parsing dead tick strings. You are reacting to human presence in real time.
The X-ray machine for audio understanding isn't murky anymore. It's finally seeing the whole picture.
It really is. Incredible stuff. Thanks for checking out this deep dive into the MOSS Audio Technical Report for AI Paper Slop. See you next time.